Okay, so we're going to start 5.2, multiplying and dividing radicals. The first two examples will be specifically multiplying, and then the last example will be division. So when you're multiplying radicals, there are two things that you need to remember. The first one being that when you multiply radicals, you multiply the coefficients and you multiply the radicands, okay, and they should be done separately. And the second thing is that you can only multiply radicals if they have the same index. Okay, they don't have to be like radicals, they just have to share the same index. And there are two approaches. On our first example here, what you do first is the multiplication, and then you simplify. Okay, and on the second one, you reverse that process. So you first simplify, and then you multiply. Okay, so I'll go through these two examples and then we'll do a couple from scratch. Okay, so on the first example here, or the first method, we want to multiply the coefficients and multiply the radicands. So our coefficients are the 2 and the 4, which we multiply here, and our radicands are the root 7 and the root 75, which we multiply together under the same square root bracket. So we're going to go 2 times 4 to give you the 8, and then within the radical sign you've got 7 times 75, which is 525. And now we will simplify the square root of 525. And here they're using the square root method, so the biggest square root that, or the biggest perfect square that fits into 525 is 25, and the remaining factor is 21. Then you take the square root of 25, which is 5, you bring it outside the bracket, and you multiply that by the 8. 8 times 5 is 40. You're left with this you're left with 21 within the square root bracket, and so you have a final answer of 40 square root of 21. In our second method, we are first going to simplify. Okay, so we're going to take a look at the root 75, and that's what we're going to simplify. Okay, and they've used the square root, the perfect square method again. So the largest perfect square that fits into 75 is 25, and the remaining factor is 3. So you'll take the square root of 25, which is 5, bring it outside the radical sign, and that gives you 5. You're going to multiply that with the 4. 4 times 5 is 20, and then you will have the remaining factor 3 within the radical sign. And so when you simplify 4 square root 75, you will get 20 square root of 3. And now you can go ahead and multiply your coefficients, multiply your radicands. And so when you multiply your coefficients, you will have 2 times 20. When you multiply your radicals, you will get square root of 7 times 3. And when you simplify, 2 times 20 is 40, and 7 times 3 is 21, so you're left with root 21, and your answer is 40 root 21. Now, I prefer to use the first method. Okay, so when I do my other examples, that's what I'll do. Of course, you're free to choose whatever method you want. So in general, if you have m k root of a times n k root of b, you would multiply your coefficients, okay, the m and the n, and you would multiply your radicals, and so square root, you'd have k root of a times b, where k is the natural number and m, n, a, and b are real numbers. Now, if your index, okay, k is the index, if your index is an even number, then remember you're going to have restrictions. So in this case, a must be greater than and equal to to 0, and b must be greater than and equal to 0. Okay? If you don't have an even numbered coefficient, or sorry, index, then you don't have to worry about that. Okay, so let's take a look at our first example. You've been asked to simplify the products where possible. So on our first example, we are going to multiply a negative 3 times the square root of 2x times 4 times the square root of 6. Notice we have an x inside the radical sign, and because our index is even, right, our index is a 2, then you need to worry about a restriction, so x must be greater than or equal to 0. Okay, so we're going to follow the rules up above. We're first going to multiply our coefficients, and then secondly we will multiply what is inside the radical signs. Okay, so we're going to go negative 3 times 4, and then square root 2x times 6. We will multiply the negative 3 times the 4, we'll get negative 12. And then inside the radical sign, 2x times 6, which is 12x. Now, 12x is not simplified, so we are going to simplify here. And I'm going to use the square root method too. Sorry, not the square root method, the perfect square method. And the largest perfect square that fits into 12 is 4. And you multiply that by 3 to get the 12, and then you have the x. And you can take the square root of 4, which is 2, and we are going to take that 2 and multiply it by the negative 12. And what is remaining inside the radical sign is 3x. So negative 12 times 2 is negative 24, and then square root 3x. So this is your answer for A. Now for B, notice there are no variables, so we do not have to worry about any restrictions. But notice that what is inside the bracket is a binomial. Okay, so what that means is we are going to be using the distributive principle to multiply this out. So we're going to take the 7 root 3 and we're going to multiply it by the 5 root 5, and then we're going to take the 7 root 3 and we're going to multiply it by the negative 6 root 3. So we're going to do mental math now. Okay, I'm not going to break it down into the steps that we did on A. So we're going to start, we're going to multiply our coefficients on our first two terms here. So 7 root 3 times 5 root 5. 7 times 5, 35. The square root of 3 times the square root of 5 is the square root of 15. And then minus 7 times 6 is 42. And square root of 3 times the square root of 3 is the square root of 9. Now we can do some simplifying. Because we can simplify the square root of 9. So we leave our first term the way it is. And we say, all right, the square root of 9 is 3. And so I'm going to go 42 times 3. And my final answer is the 35 root 15 minus 126. Okay. So C. Now we have two binomials that we are going to be multiplying together. So I'm going to use FOIL. Okay, the first, outside, inside, and last. So I will start by going 8 root 2 times 9 root 5, and then 8 root 2 times 6 root 10. And then you will go negative 5 times 9 root 5, and negative 5 times 6 root 10. Okay, so on the first one, we're going to go 8 root 2 times 9 root 5. So 8 times 9 is 72. Root 2 times root 5 is root 10. Plus 8 times 6 is 48. Root 2 times root 10 is root 20. And now we're going to go negative 5 times 9 root 5. So we're going to go negative 5 times 9 is negative 45. And then we don't have a square root on the 5, so we're just going to have root 5. And then we're going to go negative 5 times 6 root 10, so that gives us negative 30 root 10. Now, there is one radical here that we can simplify, and that is the 48 root 20, so we'll do that in our next step. Everything else is simplified. You can't simplify root 10 any more than it is, and you can't simplify the square root of 5 any more than it is. Okay, so we're going to leave 72 root 10, and then we're going to go plus 48, and then using the perfect square method, the largest square that fits into 20 is 4, so that's going to be 4 times 5. And then we're going to go minus 45 square root of 5 minus 30 square root of 10. So we will continue simplifying the 48 root 20. So we're going to take the 4, square root it, that gives us 2, and we're going to times the 48 by 2, which is going to give us 96. We are left with root 5, and then we can just finish copying this out. Okay, so the next thing that you want to ask yourself is which radicals are like radicals. Okay, now remember they need to have the same index and the same radicand. So this one, 72 root 10 and negative 30 root 10 are like, and 96 root 5 and minus 45 root 5 are like. So we're going to combine those. So 72 root 10 minus 30 root 10, 72 minus 30 will give us 42, and then root 10. And then 96 minus 45 will give us 51, and then root 5. And here is your final answer for this question. Okay, so on the next one, we have some variables. We have to worry about the w, and we're also working with an index of 3. Okay, but the rules are still the same. We first want to consider the question that we have. So notice you have a binomial again inside the bracket. So we're going to use the distributive principle. We're going to multiply the 9 cube root of 2w times the cube root of 4w, and then 9 cube root of 2w times 7 cube root of 28. Okay, so there's no, well, there is a coefficient in front of the cube root of 4w. It is a 1, so we're going to start by going 9 times 1 is 9. And then we multiply our radicals, so we're going to go 2w times 4w, which is 8w squared. And then plus 9 times 7, which is 63. And then the cube root of 2w times 28, which is 56w. Okay, so we're going to do some simplifying here. And I'm going to use the, just like we used the perfect square method on C here, I'm going to use the perfect cube method on this one. Okay. Now 8 is a perfect cube because we know 8 is 2 times 2 times 2. So the cube root of 8 is 2. And so I will cube root the 8, get the 2, pull it out of the bracket, and I'm going to go 9 times 2, and then cube root of w squared. Now I can't simplify the w squared because it's not a perfect cube. Alright, it would be if it was like w cubed or w to the 6 or w to the 9. any exponent that would be divisible by 3 would be a perfect cube. And then on the next one, I'm going to rewrite 56 so that I have a perfect cube times a remaining factor, and the largest perfect cube that fits into 56 is 8, and then times that by 7, because 8 times 7 is 56, and I have a W. Okay, so we'll go back to the beginning here. 9 times 2 is 18. Cube root of W squared plus the cube root of 8 is 2. And so I'm going to go 63 times 2, cube root of 7W, and then I will simplify that more fully on the next step. So 63 times 2 is 126, cube root of 7W. Okay, now take a look. We do have the same index on our radicals, but we don't have the same radicands, right? We've got a W squared here and we have a W here. So they're not like, and so it is as simplified as it can be. Okay, so this concludes our discussion for example number 1.
In this next example, you are asked to apply radical multiplication. You are given an equilateral triangle and it is framed inside a square as shown. So here we have our square and our equilateral triangle inside the square. The area of the square is 32 centimeters squared. Your first question is, what is the exact perimeter of the triangle? So let's write what we know on the square. We know that the area is 32 centimeters squared. We know that the sides are all the same on the square, so I'm going to assign the variable s. And we also know that because this is an equilateral triangle, and because one side of the equilateral triangle shares the same side as the square, the remaining two sides are also s. So let's start by writing out our area formula for a square, because we are given the area. And because we know the area is 32, let's plug that in for A. And now we want to solve for s, so that means we want to square root both sides, and we get that s is equal to the square root of 32. Now generally we would put a plus and minus in front of the square root of 32 when we solve for s squared, but because we have an actual object that is dealing with distance and length, we know that it's going to be only positive square root of 32 and not negative. Alright, so we're going to simplify our 32. We know that the largest perfect square that fits into 32 is 16, so we're going to go 16 times 2, that will give us our 32, that's equal to s. The square root of 16 is 4, and so when we simplify root 32, we get 4 root 2, and that's what our side length is. And so this is the side length of the square. So let's write that over here. So s is equal to 4 square root of 2. And as we've already discussed, all the sides of our equilateral triangle are the same. So each side is 4 root 2. So if we're going to write the perimeter to our equilateral triangle, that would be 3 times s, right? And so we go the perimeter is equal to 3 times 4 square root of 2. We multiply our coefficients, so 3 times 4 is 12, and then we have a root 2 left, and so our perimeter is 12 root 2. And so we write that the perimeter of the equilateral triangle is 12 square root 2 centimeters. Okay, and why do we call this an exact perimeter? We call it an exact perimeter because we are not taking the square root of 2. If we took the square root of 2, we would have an approximate number. But because we're leaving it in radical form, it's exact. If you were asked to find the perimeter to, let's say, 1 decimal place, then you would have to work out what the square root of 2 is, multiply that by 12, and then leave your answer in as 1 decimal. Okay? All right, our next question is asking us to determine the exact height of the triangle. So let's draw in a height, and the height always goes from the vertex, the top vertex of your triangle, down to the base at an angle of 90 degrees. So we will call this H. Now in this particular example, because we have an equilateral triangle, when we draw in the altitude or the height of our triangle, it will bisect the base into 2 equal parts. So one part of our base is half of 4 root 2, so that would be 2 root 2. Okay, so what we have now is a right triangle. Okay, we know that the base of that right triangle is 2 root 2. And we also know that the hypotenuse of this right triangle has a side length of 4 root 2. And we are looking for a value for the height. So by now you should be thinking Pythagoras' theorem, because we have a right triangle. And we know that the hypotenuse is always designated as c, so our formula is a squared plus b squared equals c squared. Now a and b can be any of these two sides, right? It doesn't matter whether the side which we're calling h is a or b. It doesn't matter whether the side which has a length of 2 root 2 is a or b. What matters is that the hypotenuse is always designated as a c. Okay, so I'm going to say that my a squared is going to be h squared. And then I'm going to plug in 2 root 2 for b squared, and then 4 root 2 for c squared. Alright, so we're going to now square our 2 root 2, which I'll do over on the side here. Okay, you know that that means 2 root 2 times 2 root 2, so we're going to multiply our coefficients together and then our radicands. Okay, so 2 times 2 is 4, and the square root of 2 times the square root of 2 is the square root of 4. And then you can work out the square root of 4, which is 2, so you're going to go 4 times 2, and you get 8. So when we go back to our equation here, in place of 2 root 2 squared, I can put 8. Okay, now let's go through the math in our head for 4 root 2 squared. I know I'm going to go 4 root 2 times 4 root 2, so 4 times 4 is 16. And then I have root 2 times root 2, which is square root of 4. And the square root of 4 is 2, so I'm going to go 2 times 16 is 32. Alright, so now I'll solve for h squared. I'm going to bring my 8 over to the other side. It becomes negative. 32 minus 8 is 24. Square root both sides. And I get that h equals the square root of 24. And once again, we have a side length, so we only need to worry about the positive value of that. So to simplify square root of 24, I'm going to write inside the radical sign 4 times 6. Square root of 4 is 2, and I leave the 6 inside. And so the height of the triangle is 2 root 6 centimeters. Our last question for this example is, what is the exact area of the triangle? And just so that there is no confusion, we're talking about the equilateral triangle. Okay, not our right triangle over here. Okay, area formula for a triangle is base times height divided by 2. Our base of our triangle is 4 root 2, and our height is 2 root 6. So we're going to plug those numbers into our formula. Base 4 root 2 times height 2 root 6 divided by 2. And what I'm going to do now is I'm going to reduce my 2's here because it'll make our math easier. So our area now is 4 times 1, which is 4, and then root 2 times root 6, which is root 12. I will write the root 12 as root of 4 times 3. The square root of 4 is 2. You want to take that out, and you're going to go 2 times 4 is 8, and then you're left with root 3. And so the area of the triangle is 8 root 3, and your units are centimeters squared, right? Because it's area. All right, so that concludes our discussion on example 2. Okay, so we're now going to take a look at dividing radicals, and I'm going to do an intro for this because there's a few things that we need to cover before we actually do some examples. Now, just like with multiplication, you need to deal with your coefficients first and then your radicands. Okay, you need to do that separately. So you want to first divide your coefficients and then divide the radicands, and then remember that you can only divide radicals that have the same index. Okay, it doesn't matter that they are not like radicals. What matters is that the index has to be the same. Okay, so the rules are fairly simple. You want to divide your coefficients, and then you want to divide the radicands. So in this example, let me just put my 3 in here. So in this example then, 4 divided by 2 is 2, and the cube root of 6 over the cube root of 3 can be written as a cube root of 6 over 3, because you can divide your radicands, and so you are left with 2 cube root of 2. So in summary then, if I have mk root of a and nk root of b, I can divide my coefficients first and then divide my radicands. Keep in mind that k has to be a natural number, and remember natural numbers are 1, 2, 3, 4, 5, and so on. And m, n, a, and b are real numbers. Now n can't be 0 because if you note here it's in the denominator, we cannot divide by 0. And b can't be 0 because once again it is in the denominator and you cannot divide by 0. Okay, so that's why n can't be 0 and b can't be 0. Now if k is an even number, then a must be greater than and equal to 0, and b must be greater than 0. Okay, so a is in the numerator, and remember you can't take the square root of a negative number, so a has to be greater than 0. That means that our number is positive. And a can also be equal to 0 because you can take the square root of 0, right? Because the square root of 0 is 0. Now b, on the other hand, can only be greater than 0. Okay, b can only be a positive number, and that's because it's in the denominator. Okay, it can't be 0. We already said that here, because you can't divide by 0. Okay. Alright, so one more thing that I want to discuss with you before we go into doing our examples is rationalizing the denominator. And before we do that, I just want to review with you irrational numbers. So an irrational number is any number that cannot be written in the form of a ratio a over b, okay, where b can't be 0. And once again, b can't be 0 because you can't divide by 0. An example of an irrational number would be the square root of 2. When you calculate that, you get 1.41 dot 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 to mean the number goes on and on. You should note that 1.41 dot 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 is a non-terminating and non-repeating decimal. When you have a non-terminating and a non-repeating decimal, it cannot be written as a fraction. Okay? Now, if you did have a repeating decimal, so for example 0.1 repeating, you can write that as a fraction because that's equal to 1 over 9. Okay? Just not non-terminating and non-repeating decimals. So radicals then are irrational when they are not perfect squares. So examples, root 2, root 5, root 7, etc. If it's a perfect square, like the square root of 25, you can take the square root of 25. That's 5, and so you have a rational number. Alright, so if we have an irrational number in our denominator, we want to do something that's called rationalizing. So to simplify an expression that has a radical in the denominator, you need to rationalize the denominator. So what do we mean by rationalizing a denominator? Well, let's go over to the right here. It means to convert to a rational number without changing the value of the expression. So we want to take an irrational number and convert it into a rational number without actually changing the value of the expression. How do you do that? If the radical is in the denominator, both the numerator and the denominator must be multiplied by a quantity that will produce a rational denominator. So this is kind of wordy. It's not really that bad. Okay, so let's take a look at our example. We have 5 over 2 root 3. So for an expression with a monomial square root denominator, okay, which we have here. Here is our monomial. Okay, and it's in the denominator and it's a square root. You want to multiply the numerator and the denominator by the radical term from the denominator. Okay, well, what is the radical term in our denominator? Well, it happens to be the square root of 3. So if I multiply both the numerator and the denominator by my radical, then I would be multiplying the numerator by root 3 and the denominator by root 3. Now, why does this work? Okay, well, note that root 3 divided by root 3 is equal to 1. Anything divided by itself is equal to 1. So really what I'm doing here is I am multiplying by 1. And when you multiply by 1, you do not change the value of the expression. Okay, so if you don't change the value of the expression, it's really the same thing, right? Okay, so our radical is root 3. We're going to multiply by root 3 over root 3. We are going to start by first multiplying our numerator and then multiplying our denominator. Okay, so in the numerator, we have 5 times root 3, which is 5 root 3. In the denominator, 2 root 3 times root 3. Okay, so how do we multiply 2 root 3 times root 3? Well, we're going to get 2 times the square root of 9, which is 2 times 3, because the square root of 9 is 3, which gives you 6. Okay? So when I multiply 2 root 3 times root 3, I get 6. Now notice, your denominator is a rational number. Okay, so we took an expression that had an irrational number in the denominator and we converted it into an expression that has a rational number in the denominator. These two terms are equivalent. Okay? If you take out your oops, I should put a 3 there. If you take out your calculator and you evaluate 5 over 2 root 3, you should get the same number when you calculate 5 square root 3 divided by 6. You should get exactly the same number. Okay? Alright, so what do you do then when your denominator doesn't have a monomial in it? What do you do when you have a binomial denominator that contains a square root. Okay, well, you're going to multiply both the numerator and the denominator by something called a conjugate of the denominator. Okay, so what's a conjugate? Well, two binomial factors whose product is the difference of two squares. Now, the only way that you can get the product of the difference of two squares is if you multiply a sum and a difference together. So an example, the binomials a plus b and a minus b are conjugates since their product is a squared minus b squared. So let's take a look at how that happens. We have a minus b times a plus b. Now these are considered conjugates, okay? They share the same term. One sign is minus and one sign is plus. So we have a sum and difference here. When I FOIL this, okay, so when I do the first, outside, inside, and last, I get a squared plus ab minus ab minus b squared. Notice that your middle terms are opposite signs, so they cancel each other out. They give you 0, and you're left with a squared minus b squared. Okay, so when you square a sum and difference, you get a difference of squares. There's a nice little shortcut for this. And the shortcut is this. If I'm multiplying a sum and difference, all I have to do is square the first term, so a squared, square the second term, so b squared, and my sign will always be minus. Okay? And that's because negative b times positive b will give you negative b squared. So even if I have radicals, same rules apply. Here I have a sum and difference, so they're conjugates. Okay, they share the same terms, just different signs. When I square my first term, so the square root of u squared, and minus the square of my second term, so the square root of v squared, I get u minus v. Okay, remember, squares undo square roots. So when I square the square root of u, the square undoes the square root, and I'm left with u. Same thing when I square the square root of v, the square undoes the square root, and I'm left with v. So let's do another example. Let's say that we have 1 minus root x and times it by its conjugate, 1 plus root x. Use our shortcut, square the first term, 1 squared is 1, minus the square of our second term, the square of root x is x, and so we get 1 minus x. So in the radical expression then, 5 square root of 3 over 4 minus root 6, the conjugates of 4 minus root 6 are 4 plus root 6 and negative 4 minus root 6. Now I like to work with this one better. Okay, I choose this one. Okay, both forms of the conjugate work. I'm just more comfortable with this. Notice that you have the same terms in both expressions. On the first one, you have a minus root 6 and a plus root 6, and on the second example, you have a positive root 4 and a minus root 4. Okay? These are both conjugates of 4 minus root 6. Now, if you multiply either of these expressions with the denominator, the product will be a rational number. Okay, so that's what we're going to do. We have 4 minus root 6. Its conjugate is 4 plus root 6, so we're going to multiply both the numerator and the denominator by 4 plus root 6. Remember that this equals 1, and we are multiplying by 1. Okay, and that doesn't change the expression when we multiply by 1. Okay, the value of the expression when we multiply by 1. Okay, so in the numerator, we are going to distribute the 5 root 3 over the 4. Sorry, the 5 root 3 over the 4 and the 5 root 3 over the 6. In the denominator, we're going to use our shortcut. So 5 root 3 times 4 is 20 root 3. 5 root 3 times the square root of 6 is 5 root 18. In the denominator then, we square our 4, so 4 squared minus our square root of 6 squared. Now we got two things we need to simplify. We have to finish simplifying the denominator, and we need to simplify the root 18. So 20 root 3 plus 5. The 18 we're going to rewrite as 9 times 2. We can square root the 9, we get 3, take the 3 out of the radical sign, times the 3 times the 5, we get 15, and we're left with 15 root 2. So now in the numerator we have 20 root 3 plus 15 root 2. In the denominator, let's finish this up. 4 squared is 16, minus root 6 squared is 6. 16 minus 6 is 10. And then I'm going to show you how to simplify this. Okay, so how do we get from 20 root 3 plus 15 root 2 over 10 to 4 root 3 plus 3 root 2 over 2? Well, what I notice is that I have a common factor in my numerator, and my common factor is a 5. I'm going to pull that out. And I am left with 4 root 3 plus 3 root 2 inside the bracket, and then I divide that by 10. And then I can divide 5 into 5 once and into 10 twice, and so I would get 4 root 3 plus 3 root 2 over 2. Now let's take a look at this example. Let's say we had 20 root 3 plus 19 root 2 divided by 10. This expression is already considered simplified. Okay, and that's because we don't have a common factor in our numerator, okay? The 20 and the 19 do not share a common factor outside of 1, okay? So for those of you that like to do this, you can't do that. No. Okay? In other words, 2 root 3 plus 19 root 2 is not the answer. Okay? You can only do this kind of reducing if you can also reduce both terms in the numerator. Okay? So the second term in the numerator should be reduced also. It's much better if you just pull the common factor out of the numerator and then simplify with the denominator. You're less likely to make mistakes when you do that. Okay, so that concludes our discussion on rationalizing the denominator. In our next video, we will do the examples for dividing radicals. Okay, we're looking at division of radicals, example 3. We have 4 examples here. We're going to start with a fairly easy one and move our way up to one that's a little more complicated. Okay, if you take a look at the one, our first example here, A, notice that your denominator can divide evenly into your numerator, okay? Now, that's only true, of course, if we have the same index, which we do. And if you notice that your denominator divides evenly into your numerator, you can just write it under the same radical sign. So 24x squared over 3x. And then do the division. 24 over 3 is 8. X squared over x is x. And then we can simplify the 8. Let's write it as 4 times 2. Square root of 4 is 2. So we pull it outside the radical sign, and we are left with 2 square root of 2x. Now, let's take a look at our restriction. When we say that x is greater than 0, we mean that we have a positive number. Okay, now that's important when we have an even index, right? Because you can only square root a positive number. And so we have to indicate that whatever number x is, it must be positive. Now, notice it doesn't read x is greater than or equal to 0, all right? It doesn't read equal to 0, okay, because x cannot equal 0. And why can x not equal 0? Because it's in the denominator, and we cannot divide by 0. Okay, so that's why we just write x is greater than 0 and not x is greater than or equal to 0. Okay, so let's take a look at b. Now on b, notice that your root 2 doesn't divide evenly into 5 root n. So we're going to approach this question slightly different. Notice we have a monomial in the denominator. And notice we also have a radical in the denominator. And when we have a radical in the denominator, it cannot be considered simplified. So in this case, we are going to want to rationalize the denominator. Okay, and in this case, by multiplying by, and because our radical in our denominator is root 2, we are going to multiply by the square root of 2 over the square root of 2, right? Because we know that this equals 1. Okay, and when we multiply by 1, we don't change the value of our expression. So I'll rewrite the question for square root of 5n over 3 square root of 2. We're going to multiply by the root 2 over root 2. So I'm going to go 4 root 5n times root 2, and that's going to give me 4 square root of 5n times 2, which is 10n, over 3 times root 2 times root 2, which is 2. And so I get 4 square root of 10n over 6, which I can simplify to 2 square root of 10n over 3, or 2 over 3 square root of 10n. Okay? Okay, let's take a look at our restriction. Notice this time it says n is greater than and equal to 0. Now we have a restriction because our index is an even number, and n is greater than 0 means that n has to be positive, and equals 0 means that we can have 0 as a number, possible number for n, and that's because you can take the square root of 0. And we can also include 0 too because we don't have a variable in our denominator, so there's no restriction about dividing by 0. Okay? Alright, so let's take a look at our next example. This one here, we have a binomial in our denominator. And our binomial has a radical. And so when you have a binomial in your denominator that has a radical, you should be thinking conjugate. So what is the conjugate of square root of 5 plus 7? Okay, well, the conjugate of the square root of 5 plus 7 is the square root of 5 minus 7. Okay, so remember, same terms, just opposite signs. Okay, so I'm going to multiply both the numerator and the denominator by my conjugate. Alright, because that's the same as multiplying by 1, and therefore I don't change the value of my expression. And I'm going to multiply, so I'm going to put some brackets in. So I will distribute the 11 through the numerator, and I will use my shortcut method to simplify the denominator, right, because I have a sum and difference. So in the numerator, I'm going to have 11 times the square root of 5, which is 11 root 5, minus 11 times 7, which is 77. In my denominator, square my first term, root 5 squared is 5, minus square my second term, 7 squared is 49. Simplify the denominator. 5 minus 49 is negative 44. Okay, so you should note now that I have a common factor in my numerator that I can reduce with my denominator. So my common factor in my numerator is 11. And I am left with root 5 minus 7 in the numerator. And then I 44 in my denominator, and so I can simplify, right? 11 goes into 11 once, 11 goes into negative 44 negative 4 times. And so I now have root 5 minus 7 over negative 4. Or I can bring the negative up into the numerator. And I am left with negative root 5 plus 7 over 4. Okay. Okay, so in our last example, we have two things going on. Number one, we have a monomial in the denominator, but it is a cubed root. Okay, and in the numerator, I have a square root. So even if 6 could fit into 11, I wouldn't be able to divide these two radicals because they don't share the same index. So that's the other thing that's going on. Okay. All right, notice our restriction said that y can't be 0, and that's because you can't divide by 0. Okay, that's because y is in the denominator. Okay, so how do we rationalize a denominator that has a cube root? Well, if you remember from the past, if I cube a cube root, the cube undoes the cube root, and in this case, if I'm cubing the cube root of 6, I am left with 6. So if I want to rationalize this denominator, I need to make sure that I am cubing whatever the radical is in my denominator. Okay? Alright, so let's start. We've got 4 root 11 over y cube root of 6. Now, I know that I have to multiply the cube root of 6 by itself 3 times, because that's the only way that I can rationalize the denominator. So if I have to multiply by the cube root of 6 times the cube root of 6 in the denominator, I'll have to do the same thing in the numerator. And you know what? I'm going to do this with a different color, just so it stands out a little more. So okay, so I've got cube root of 6 times cube root of 6 divided by the cube root of 6 times the cube root of 6. So this whole expression here that is in red is equal to 1. So I'm not changing the value of my original expression. Okay, so what I'm going to do now, I'm going to do the multiplication. Now I can't multiply two radicals that don't share the same index. So the numerator, when I simplify, I'm just going to get 4 root 11, and then I'm going to go cube root of 6 times the cube root of 6, and I'm going to get times the cube root of 36, right? Because I can go 6 times 6 is 36. In the denominator, I'm going to have y times. Now we already know from up here that when I cube the cube root of 6, I get 6. So I'm doing that. I'm going the cube root of 6 times the cube root of 6 times the cube root of 6, and I know that's going to give me 6. Okay. Okay, now I still can do some simplifying. All right, I can see that 2 goes into 4 twice, and it goes into 6 3 times. So my final answer is going to be 2 root 11 times the cube root of 36 divided by 3y, and that is my final answer. Okay, so that concludes our division of radicals.